Hi there again, this is Mr. Sand. We're going to talk about energy, we're going to talk about kinetic energy and work right now. So last time we defined work at an angle. That was pretty cool. So it was work equals, I think it was this. Yeah. So it was force times the cosine theta times the displacement. And more generally, that was at a force applied at an angle. So work equals force times displacement. So today I'm going to try to convince you that work equals the change of kinetic energy. So before I get into that, I'm going to have to define what energy is and what kinetic energy is. And then when I'm done with that, I'm going to try to motivate it to you. Uh, I'm going to motivate it. I'm going to motivate that with equations, and then I'm going to go through a warm-up problem and talk to you about how that kinetic energy, that change in kinetic energy, can be then converted back into force or displacement through work. It's pretty cool. So let's get started. Energy. What is energy? You've probably heard that word tossed about all over the place. Energy. It takes energy. What is energy? Energy, just very, very, very broadly defined here. Okay, this is not even a close attempt at a rigorous definition. I'm not even going to try, but I'm going to try just to give you a general idea, a flavor, if you will, for what energy is. Energy is an object's ability to change itself or the external world. So it's an ability to change. So you have a certain amount of energy, you have a certain amount of ability to change either yourself or the external world. That is energy. Ability to change either yourself or the external world. That should make some intuitive sense. Kinetic energy is energy due to an object's motion. So it's the ability to change either itself or the external world due to its motion. So you've got something moving and it can change either itself or something else due to that movement. That is kinetic energy. And kinetic energy we define as this is kinetic energy, so I'll put kinetic energy up here. Kinetic energy equals 1/2 mv squared. That's kinetic energy. Right. So how do we get from this kinetic energy right here, this is, well, I abbreviate kinetic energy KE, to the change of kinetic energy equals work? That's weird. It doesn't seem like it should fit at all. Well, let's go back to an earlier equation. The earlier equation we had, this is all the way back in Unit 2, when we're talking about acceleration. And we said that S, we call it delta S at the time, but it's really just S. S equals VF minus the initial velocity, and both of these were squared. Squared. It's a minus sign, over 2a. So we're going to start with this equation, and we're eventually going to get over here. Trust me. So we'll start off with that. And the first thing I want to do is I want to replace this a with something a little bit more useful. So we'll use our F equals ma, praise Newton. And I want to rearrange this around so I can get just a by itself. So to do that, I'm going to take m divided by both sides. So it's going to be F. All right, divide both sides by m. F over m equals a. So I'm going to take this right here, and I'm going to plug it in right there. So let me rewrite this. S equals VF squared minus U squared all over 2 times F over m. That looks pretty cool. So now I'm just going to do some rearranging magic here. I'll multiply both sides by Fm, or F over m. So if I multiply both sides by F over m, this side will drop out, and it'll leave me with F over m times S. Put these in parentheses just to make it feel nice. Over, it'll be F VF squared minus U squared over 2 Looking good so far. Now I want to get F by itself over here with S. So I'm going to multiply both sides by M. So that'll leave us with Fs on this side. Ooh, this is looking like work. Fs on this side equals Vf squared minus U squared over 2, and this whole thing times M. This looks great. But I'm not done yet. I'm going to make this look a little prettier. So I'm going to just, I'm going to take this divided by 2 right here, this denominator, yeah. And I'm going to do this. I'm going to just make it look a little bit more tidy. Vf squared. And this whole thing is multiplied by m. So I'm going to say this is times m minus 1/2 u squared times m. Ah, all right. So what I did there is I took 1/2 and I multiplied by each one of these terms, and I multiplied each of those terms times m. I just rewrote this side. And this whole thing still equals Fs. Okay. This is fantastic because Fs, look at that, it equals work. So I'm just going to put this as work equals, oh, look at this, mv squared. What? Oh my god, it's right there, 1/2 mv squared. So this is 1/2 mv squared. I'll rewrite this again, minus 1/2 mu squared. And u, remember, is just the initial velocity. So they're really both velocity. And this kinetic energy right there, that's velocity. This is also velocity. It's just the initial velocity. So what I can say is I can actually say this is the final kinetic energy minus the kinetic energy. That's the initial kinetic energy. That equals work. And if I do that, then, oh my god, work equals the change in kinetic energy, and that's what we're going for, which is really strange, I think. Work, so the force applied at a distance, so force applied over a distance equals the change in kinetic energy, the final kinetic energy minus the initial kinetic energy. Okay, so that is just a fantastic result. It's a fantastic result because now we can say that, well, this change in kinetic energy, if we need to, this change in kinetic energy equals work. Well, it also equals, work also equals force times displacement. So if we're given, and you'll see this in a couple problems here, if we're given something like the mass and the velocity of an object, and the final and the initial mass and velocity of the object. I'm just rewriting, I'm just spelling this change of kinetic energy out right here. If I'm given this and this, then I can find out what the force times the displacement is. Let's say that I know that this is taking place over a certain distance, then I can know what the force is that's applied here to get that change in kinetic energy. Or if I'm given the force, I can find out how far you've gone if you know what the change in kinetic energy is. It's pretty cool. So let me do a quick problem, a quick warm-up problem. Number 1, 105 gram hockey puck, which let's just automatically change that to something else. Of course, we want to change this into kilograms. And I don't know if I've told you this before, but the units for work and for changing kinetic energy and all energy is joules. Joules is what we use as an abbreviation for our unit, which is really newtons times meters. That's what a joule equals. And that should make sense because it's newtons, which is force, and the distance, which is given, or the displacement, which is given in meters. Okay, so we've got a 105 gram hockey puck, which is really a 0.105 kilogram hockey puck. That's our mass. Moving across the ice, and a player exerts a force over 0.150 meters. So we know what our S is. S is 0.15 meters. Great. If the puck was moving at 2.5 meters per second and the player accelerates it to 4.3 meters per second, so we know what our initial velocity is. Our initial velocity is 2.4 meters per second, and our final velocity, Vf, is 4.3 meters per second. The question is, how much work does the player do on the puck? Assume no friction. So we're accelerating with the motion of this puck. This should be pretty easy. So the puck is moving on the ice. The force is being applied in the direction of its movement. So we're all good. We don't have to worry about this cosine here. We can just say, fine, the work is the change in kinetic energy. The change in kinetic energy is 1/2. Well, we know what it is. It's this over here. But I'll just write it out. Vf squared minus 1/2 mu squared. We know all of those variables from over here. That's awesome. So we don't even need the distance. That's so cool. We don't even need the distance. We'll need it for part B, but not for part A. This is part A. So if you plug all those values in, you should get as a final answer 0.67 joules. That's our final answer. Now for part B, which I'm going to write over here, we'll do part B over here. This is part A. This is part B. Real quickly, it says how much force does the player use to push the puck? Assume no friction. So now we're worried about force. Well, we know that force, look at this over here. We know that force times displacement equals work. So if we know the work done, and we know the displacement because it's given to us right here, we can figure out the force. So over here, we've got work equals force times displacement. So if we know displacement and we don't know force, we'll just rearrange this. So it'll be work divided by displacement will equal our force. So this is going to be 0.67 joules divided by displacement, which is 0.15 meters. And we're going to get our force. And our force is 4.5 newtons. So this is just a little taste of how these equations kind of go back and forth with each other. All right, that's all we have for this section. It should be fairly easy for you. Good luck.